So we found with our harmonic series of 1 over and the series 1 over n squared, the infinite series, that our divergence test proved inconclusive. So it becomes, well, where do we go from there? Where do we go now? Well, if your series is, and at this point you've done enough integration to know, can I easily integrate? We do have something called our integral test. So that's what this video is going to be about. It's going to be specifically about the integral test. Now, the hardest part about the integral test is you need to make sure that your function you're going to create, because that's what we're going to do. To take an integral, you have to have a function. Remember, we have infinite series. So we kind of have to turn our infinite series into a function. This function must meet 3 criteria. So to perform an integral test, you essentially convert your series a to the n to an f of x function. Okay? And what we're going to do is look at the behavior of the function. All right? But in order to perform the test, that function must meet 3 criteria. So your new f of x must meet 3 criteria, assumptions, whatever you want to call them, and you need to check this. You don't need to do a formal check or a formal proof, but you have to do enough of a check to know that you can move forward with your integral test. So the first one is, well, it needs to be continuous on the domain. All right? On the, let's call this the restricted domain. All right? And that depends on your original series, but it often looks like 1 to infinity, for example, anything like that. It's okay if it's not continuous outside the domain, your restricted domain, but it needs to be continuous on that restricted domain. Okay, second thing, it's got to be positive. It needs to be a positive function, again, along that restricted domain. And the third thing, it must be decreasing. So the positive is usually you can check pretty simply just by looking at it, and we'll go over that. The decreasing part, again, you can sketch it if it's easy to sketch and see that it's decreasing, or if its derivative is less than 0 on that restricted domain, that's another way to show that a function, of course, is decreasing, because that means any function, if you recall, that is decreasing is always going to have a negative slope. All right, they kind of went hand in hand, and we examined that back in Calc 1 in Chapter 4, applications of derivatives. Okay, so here's the deal. If all this criteria is met, then our original infinite series, I'll call it k equaling 1 to infinity of a sub k, and our newly formed function that we form from the series either both converge or both diverge. So what does that mean? Essentially, if the function converges, the series converges. If the function, the integral from 1 to infinity of the function diverges, the infinite series diverges. Now, here's the kind of, there's always a catch with all of these, all right? The diverging is fine. If the function, the integral of the function, 1 to infinity, diverges, then yes, your series diverges. If the integral of the function converges, your series also converges, but they do not converge to the same value, and that's important. But if your function converges, then your infinite series also converges, but not to the same value. Not to the same value. Because remember, the integral is the area under the curve. The series is the summation of each discrete point. So they're not going to be the same value, but if one does converge, the other also must converge. And here's the tricky part. Only, and I keep repeating things throughout the video, so remember them, your geometric and your telescoping, were we able to find the values that our series converge to? In most of these series, all you're determining is that they converge. You're not looking for the actual values they converge to. For a lot of these series, it goes beyond the scope of what we have learned up to this point, and you'll come across that in a more advanced calculus class. All right, so now let's take a look using this integral test, and let's go back to our harmonic, which is n equals 1 to 1 over n. Very basic that you're just going to now know after this, but at least we can use it to show how the integral tests work on something that we are somewhat familiar with. All right, so I'm going to take the summation of n equaling 1 to infinity of 1 over n. It's our harmonic series. What does it look like again? It looks like 1 plus a half plus a third plus 1/4 plus ... into infinity. All right, so let's go ahead. And the first thing you're going to do is write it as a function. So what does it look like as a function? Well, all you're doing is swapping out the n for an x and calling it an f of x. All right, because we're going to use the function to determine the convergence or divergence of the discrete infinite series. All right, our checklist. Remember, all right, what is the domain of this new function? The domain is going to come from here. We are only looking at this from 1 to infinity. So getting that domain is important, and we'll call it a restricted domain because we're restricting our domain to what it is in the series, which is 1 to infinity. In other words, I don't care what happens before 1. Because the actual domain of the function 1 over x is basically negative infinity to 0 and then 0 to infinity. The only issue is obviously when x equals 0. And sometimes it is helpful to also have a sketch. So, you know, this is our function of 1 over x. But because I've restricted the domain, I only need, right, that part. Okay, so that's the idea. Again, I'm looking for that you actually thought about each piece. When you are determining if a function is continuous, what you are really looking for is, well, where is it not continuous? All right, what are the issues with this function? Well, the function 1 over x, we already determined it is not continuous when x equals 0. But here's the nice part. 0 is not in our restricted domain. Since 0 is not there, it is continuous on every value from 1 to infinity. So we can actually say yes. Continuous on 1 to infinity. So we're good. Again, not looking for a major proof. Just show me you thought about it. Second piece. Is it positive? Well, there are no negative signs in our function, right? 1 over x is positive. That one is kind of obvious, right? We're only plugging in positive numbers to a function that has only positive values. So yes, it's going to be positive on the whole thing. And is it decreasing? So there's two different ways. If you're able to show me the sketch, yeah, I can see it's decreasing. Yes, I'm good. But if you come across a function where you can't show the sketch, kind of the easiest and quickest way to do decreasing, if that's 1 over x, which is f of x equals x to the negative 1, not inverse, sorry. I don't know why I wrote inverse. F prime of x, well, is what? Negative 1 times x decreased to the negative 2. So here's the deal. We know this. If a derivative is negative, as this derivative is, because this equals negative 1 over x squared, right? If our derivative is negative, then our function must be decreasing. So yes, again, if you can show me a sketch, show a sketch. If not, just do the derivative real quick. But you got to check. This has checked. Boom, boom, boom. All the boxes. Once it checks all the boxes, go ahead and find the limit. So now we want the limit, and it's an improper, right? Because we're taking b to infinity. We want the limit, technically, we want the integral here. I'll get rid of the limit for a second. We want the integral from 1 to infinity of f of x, right? Well, that's going to be the limit as b goes to infinity of 1 to b of 1 over x. Okay? And I know, we did this. We did this problem when we did improper integrals at the end of chapter 8. It was like 8.9, I believe. So, that's the limit as b goes to infinity of ln x from 1 to b. Finish it out. Of ln b minus ln 1, right? Ln 1 goes to 0, but when you put in infinity, the natural log of a number as that number continues to increase and go to infinity actually is infinity. Okay, so that means the improper, which we found at the end of chapter 8, the improper fraction diverges. So therefore, by the integral test, the summation n equaling 1 to infinity of 1 over n diverges. Okay? We're going to summarize this one, the last, which will be very short. The last video for 10.4 will be on a generalization of p-series, and we'll generalize this idea. Let's real quick do the same thing, but this time let's do it with n equal 1 to infinity of 1 over n squared. All right, so to apply the integral test, because number one, we already found out that the divergence test is inconclusive. Pretty easy to find the integral of this one, so we're going to apply the integral test. Okay, well, our function is 1 over x squared. For the same reasons that 1 over x is continuous, x is continuous, 1 over x squared is indeed continuous. We're good on the domain. Because remember, we are again restricting our domain from 1 to infinity. The only issue is when x is 0, and that's not part of our domain, so it's continuous. Yep, definitely positive. Number one, any value we put in is going to be squared, so it's going to make it positive, but we're on a domain of only positive numbers, so it's positive. We don't even have to do anything there. And the graph, or if you went ahead and found the derivative, you would see that the derivative is negative. It is decreasing. Okay, so because of all that, we can go ahead and look at limit of 1 of the integral as b goes to infinity, 1 to b, 1 over x squared dx, which is the limit as b goes to infinity, and 1 over x squared, which is x to the negative 2, right? Which becomes x to the negative 1 over negative 1. That's the integral from 1 to b. So it's the limit plug in b. So it's negative 1 over b minus negative 1 as b goes to infinity. This first term goes to 0, right? 1 over infinity is 0. So it becomes 0 plus 1 equals 1. Now, all we care about when we're talking about the integral, the improper integral going to infinity, is that the limit as b went to infinity converges to a number. Okay? Doesn't matter what that number is, because remember, the series isn't going to have the same number it converges to. We just want to say, that converges. Doesn't matter that it's a 1. Because that converges by integral test, you've showed me you can use the integral test by doing the checklist. You've shown the integral test. The series n equaling 1 to infinity, 1 over n squared converges. It does not converge to 1. In fact, you can see real quick that it's not. Because remember, the limit part, this part here represents an area under a curve. We know this does not converge to the number 1 because when you go and plug in, you can see right away it's going to be 1 plus 1/4 plus, when you plug in 3, you get 1/9, so on, so on, so on. So it clearly converges to a number greater than 1. And again, we're not concerned at this point what it converges to. We just want the steps to understand that it converges because the function it's related to converges. Okay? All right, let's, we will come back again in it'll be a very short video. We will come back to these types of series, but let's use our integral tests on a different series. So for example, let's suppose I had and if you're given this, you might actually try the divergence test first, right? That we did in the last video. And if you attempt the divergence test, then you're just taking the limit as n approaches infinity of 1 over square root of 2n minus 5, right? Well, you know, once you plug infinity into that denominator, I don't care if you multiply it by 2, subtract 5, and then take the square root, it's still going to be 1 over infinity, which means your divergence test equals 0, making it inconclusive. And if you were taking a test and you came across this, I'd kind of expect to see that written down somewhere, because you should always just start with your divergence test. Because if it didn't equal 0, you're done the problem and you can move on, right, to the next problem. So I would expect to see this on a test. Where you go from there, depends on the actual problem. So for this one, well, we're fine. We can indeed take an integral. So we might as well just apply the integral test. Now, here's what's cool about this convergence and divergence. It really doesn't matter. Don't get too caught up with the fact that we're not starting at 1. Because when we really look at convergence and divergence, we really care about what's happening at the end of our series, in this infinite series, not what's happening at the beginning. So don't get caught up on the k equals 3. There is a reason for that, and we'll see in a minute. Because now, when you go and turn this into a function, right? What is my new restricted domain? I'm going from 3 to infinity. That is important. That's important when you do your first part of your checklist, which you are checking if it's continuous. I'll say it again. Best way to check if a function is continuous is to determine where it's not continuous. So, where is my function not continuous? Well, I have a rational expression in 2x minus 5, right? But it's under a radical. So that value can't be negative. So if that value is less than 0, it's not continuous. But here's the thing. It's also in a denominator. So not only can't it be less than 0, it can't be equal to 0. Because if my function 2s minus 5 is less than or equal to 0, I don't have a continuous function. So it's important to kind of take note, where does that happen? That happens whenever my x values are less than 2.5. Hey, but here's the good part. I'm starting at 3. So anywhere above 2.5, I'm good. I have a continuous function, so I just checked a continuity. We're good with continuity. Is it positive? Honestly, just by the sheer definition of a radical, value on that domain is going to be positive. Yes, it's always going to be positive. And 3, you can check for decreasing. And if this one you're not too sure of, all you have to do is quickly look at its derivative. So the original function is 2x minus 5 to the negative 1/2 power, which means the derivative is negative 1/2 2x minus 5. I decrease it to the negative 3/2 power. Well, there you go. Since my derivative is negative, my function decreasing. I am good on my checklist. So it doesn't take long. Just a few quick notes, not a lot of work. I just went through it. Writing this down on the test, what I wrote right here shows me you thought through the checklist. Okay? So now I just got to take the limit, right? Or the integral, the limit of the integral. So it's the limit as b goes to infinity, because it's an improper integral, of 3, I'm starting at 3, to b, right? Because it's an improper integral of my function 2x minus 5 to the negative 1/2. So you do have to find this integral. To get this integral, you do need a little bit of u sub, because we're just going to put it in there. You need the derivative of 2x minus 5, so you need a 2, which means I need a 1/2 out here. I can apply my u sub, then I can put my function back in. If you want to take the time to do out the whole u sub, please do so, but we've done this enough now. So this is going to be 1/2. I'm going to pull the 1/2 all the way out, because it's really not, in the end, going to matter. And, forgot to write. Well, yeah, we'll put the 1/2 out there. Yeah, limit b goes to infinity. When I take that integral, it's actually a 2, because it's divided. It goes up to a half divided by 2, so it's 2x minus 5 from 3 to b. So here's what's nice. The 2 and the 1/2 just do away with each other. Don't need to worry about those. So I have the limit as b goes to infinity of 2b minus 5 I forgot the radical part. That's fine. 2b minus 5 minus the radical of 1, right? So when you plug in infinity, you're basically getting infinity minus 1, which is infinity, so it diverges. And then our final statement is to say, by the integral test. And you can only say this now is because you've already shown me the checklist that I could use the integral test. By the integral test, this series, n equaling 3 to infinity, what was it again? K, it was k to infinity, 1 over 2k minus 5. Diverges. Okay. So that's your integral test. Integral test is great after you've applied the divergence test. You get an inconclusive result. Your function doesn't fit like anything like a geometric telescoping, something you're familiar with, and we're going to generalize one more in the next video. So, but it is easy to integrate. If your series is not easy to integrate, you're not going to use the integral test. Don't worry. There's more tests that we'll learn in future sections. But for now, if it's easy to integrate, you can go ahead and utilize that integral test. Just don't forget to show me real quick that it meets the criteria. Find that improper integral. And don't forget to state which test you use when you give your final answer.